In this work, we introduce Sphere, a simulator for photorealistic embodied AI research. At its core, Sphere is a Python library that can connect to and programmatically control any Unreal Engine application via a modular plugin architecture. Sphere exposes over 14,000 unique functions to Python, representing an order of magnitude increase in programmable functionality over existing Unreal-based simulators. Additionally, a single Sphere instance can render photorealistic beauty images directly into a user's NumPy array at over 150 megapixels per second, which is an order of magnitude faster than existing Unreal plugins. Let's look at some applications we implemented using Sphere. In this application, we execute two simple Sphere programs to control a human and a car in a photorealistic city environment. Here we simulate time of day changes in a photorealistic outdoor environment. Sphere can also manipulate Unreal's procedural content generation systems, or PCG systems for short. Here we translate the main PCG entity in this scene from left to right. Notice how the PCG entity harmonizes with the rest of the scene in a convincing way as we translate it. Sphere can also be used in co-simulation applications with external physics simulators. In this application, we interactively control the MuJoCo physics simulator using the default MuJoCo viewer. In real time, as the MuJoCo simulation is running, we query the state of the MuJoCo scene, and we use Sphere to update the state of a corresponding Unreal scene. Any entity that can be controlled with Unreal's input systems can be programmatically controlled with Sphere. Unlike existing Unreal-based simulators, Sphere does not make any assumptions or impose any restrictions on an entity's action space. Sphere can also be used to script detailed gameplay logic and control many agents simultaneously. In this application, we execute a Sphere program to script a variety of gameplay events in a simple resource collecting game. We increase the amount of resources the player has, find a suitable location on the map to build a new structure, spawn several agents, and assign those agents to build the structure. Finally, Sphere can be used by AI coding assistants to manipulate scenes in response to user text prompts. In this application, we implement a connector between Claude Code and Unreal, such that Claude Code can manipulate Unreal scenes by writing snippets of Sphere code in an agentic loop. Before we get started here, notice that we launch a new Claude Code session, so we are not providing any hidden context that would help with this task. We begin with a simple text prompt. I have an Unreal instance running. What am I looking at? Next, we describe a simple scene modification. Let's move the vase so it is sitting on the coffee table. Okay, great. Now let's move the chairs so they're close together but not quite touching. Now let's shine a spotlight at a reasonable brightness from overhead on the vase that I'm looking at. Okay, great. Now let's spawn another couple of vases and place them next to this vase on top of this cabinet structure. Now let's swap the material of the floor and these vases. Actually, that looks a bit weird. Let's swap back. Okay, great. Finally, let's move these chairs so they're all placed next to each other along the wall on the right, all facing left. Sphere includes a highly configurable default camera sensor that provides unique ground truth image modalities that are not available in any existing Unreal-based simulator. For example, the Sphere camera sensor provides a non-diffuse intrinsic image decomposition, material IDs, and physically based shading parameter images that indicate ambient occlusion, roughness, and metallic values at each pixel. Sphere introduces an expressive high-level programming model that enables users to specify complex graphs of Unreal Engine work, with arbitrary data dependencies among work items, and to execute these graphs deterministically within a single Unreal frame. We demonstrate our programming model with a simple example program that spawns a set of coordinate axes in an indoor environment. In the Sphere programming model, graphs of Unreal work are specified as transactions. The user specifies a transaction by defining a begin frame context followed by an end frame context. Within each context, the user specifies a graph of Unreal work simply by implementing it as Python code. Each begin frame block is guaranteed to execute at the beginning of a single Unreal frame, and its corresponding end frame block is guaranteed to execute at the end of the same frame. Every C++ function and variable that is visible to Unreal's runtime reflection system, like the setActorScale3D function shown here in red, can be accessed as though it were a native Python function or variable. There are over 14,000 functions and over 53,000 variables that can be accessed this way. It is also trivial to expose new C++ functions and variables to Sphere, and this can even be accomplished without modifying the Sphere codebase. For more details, see the paper. We also provide an asynchronous variant for every function in Sphere, like the async.getComponentLocation function shown in orange. These asynchronous variants avoid synchronizing with the Unreal game thread and can therefore be used for increased efficiency. For more details, please see our paper and our public code repository. Thanks for watching.